Good morning, Algebra Essentials class. Today we are going to talk about simplifying radicals, just a basic concept that you guys need to have, especially moving on into geometry and Algebra 2. It's section 9.3, simplifying radicals. As a quick warm-up, you remember square root of 25 is just, and what we're asking ourselves is, what multiplied by itself gives us 25? So what multiplied by itself gives us 25? The answer would be 5. In reality, there is another answer to that. We could say -5, but when we're talking about just evaluating or simplifying an expression, we usually just give what they call the primary root, the positive one, right? If it was an equation where there was an equal sign and we were solving for x, we would give both answers, positive and negative. Okay, so negative square root of 100. This is like saying -1 out front, right? This is like saying -1 times the square root of 100. And the square root of 100, what multiplied by itself gives 100. So we're just like saying -1 times 10. -1 times 10 is -10. So when that negative is out front, you just include it with the answer. Square root of 16 times square root of 4. Well, square root of 16 is 4 times square root of 4 is 2. And what do we have? An answer of 8. 2/3 times the square root of 9. So that's 2/3 times 3. And I could say 3 over 1 if you want. 2 times 3 is 6 over 3. Gives us, let's go over here, 6 over 3 gives us an answer of 2. Square root of 100 over 5. Square root of 100 is 10. So what do I have here? 10 over 5. And that answer is 2. Okay? All right, so that's a warm-up. Properties of radicals, okay? There are two that we're going to deal with today. The product property says this: if I have the square root of a number times a number, or in this case we're representing them as variables, square root of the product of two numbers, it's equal to the square root of one of the numbers times the square root of the second number. So for instance, let's say I have square root of 4 times 5. That gives me the square root of 4 times the square root of 5. Right? I can break it up into two different radicals. So what do I get for an answer? 2 square root of 5. Notice that the number that's a perfect square, I actually write it as an integer. Square root of 4 is 2. Square root of 5 is irrational. It's not a perfect square. I just leave it as a square root of 5. Square root of a over b, we can break it up into, this is the quotient property, square root of a over b is equal to the square root of a divided by the square root of b. So for instance, if I have the square root of 9 over 25, square root of 9 over 25, I can break that up into the square root of 9 over the square root of 25, which gives me 3 over 5, right? Square root of 9 is 3. Square root of 25 is 5. I get an answer of 3/5. Okay? All right, so what does that mean for us? If I want to simplify a square root, and I have, say, the square root of 25, what I can do is I can break up that, I'm sorry, not square root of 25, square root of 50. If I have the square root of 50, what I want to do is look at that number 50 and ask myself, are there any factors that are perfect squares? So what are the factors of 50? 1 times 50. Now, yes, 1 is a perfect square, but it's not going to help us any to break the square root of 50 up into the square root of 1 times the square root of 50, because I'm just going to end up with 1 times the square root of 50, which is the same thing. It didn't simplify any. We weren't able to break it down and simplify it. So the other way, what I want to do then is check the other factors. So I have 2 times 25. Okay. 25 is a perfect square, right? So I'm going to break this up into the square root of 2 times the square root of 25. Right? Square root of 50 becomes the square root of 2 times the square root of 25. Square root of 25 is 5. So I have square root of 2 times square root of 5. And what I do is I just rewrite that as 5 times the square root of 2. You always write the square root last. That's your answer. Very simple. Okay. So again, figure out what your factors, the factors of the number under the square root are, and look for factors that are perfect squares. Okay. Square root of 48. All right, well, what are the factors of 48? 1 and 48. That's not going to help us. 2 and 24. Neither one of those are perfect squares. 3 and 16. Those are perfect squares. So how did I come up with that? If you have a calculator, it's real simple. Just run through the factors. Right? So what is 48 divided by 2? It's 24. So that's 2 and 24 are the factors. But that wasn't a perfect square. So what do? We take 48 and we divide it by 3. Oh, 3 and 16. Those are factors of 48. So 3 times 16 are factors of 48, and again, 16 is a perfect square. We've talked about perfect squares before. Hopefully you guys recall that. So I'm going to break the square root of 48 up into, and this is that product rule, square root of 3 times the square root of 16. Okay, square root of 3 is just the square root of 3. That's not a perfect square. Square root of 16 is 4. Oops. And we always write the square root last, so I'm going to rewrite this as 4 square root of 3. Okay. Square root of 12. So again, factors besides 1 are 2 and 6. 2 times 6 is 12. There are no perfect squares there, so 3 times 4. 4 is a perfect square. So I'm going to change this to the square root of 3 times the square root of 4. Okay, square root of 3, again, is not a perfect, it doesn't have an integer answer. It's an irrational number. We leave it as a square root. Square root of 4, though, is 2. So this is the square root of 3 times 2. I'm going to rewrite that, put the radical last. So 2 square root of 3, and that's your answer. Okay. Now, I'm going to go back here real quick. Nah, I'm going to leave it like this. So there is another way to do these. And I'm going to I'm going to show you that way right now. So let's do the same problems, and we're going to look at it a little bit differently. If I have the square root of 50, if you guys remember doing factor trees, that's what we're going to do here. And anytime we have pairs of factors, they can be written in the answer without a square root symbol. And anytime we have just a single prime factor, we can write it back underneath a square root symbol and then kind of combine terms. So what I mean by that is what are the factors of 50? And you can think of any factors in this case. But the one that comes to mind real quick is very simple, 2 and 25. Okay? And then 2 can't be broken down any further, but 25 can, so we're going to rewrite that as 5 times 5. Okay? Now, in order to come up with the answer square root of 50, we look for pairs of numbers. So I circle any pairs of numbers, and when I have a pair, I can write one of those numbers in the answer without a square root symbol. Any numbers that are left over without a pair, we put in a box, and they go back under a radical. Square root of 2, right? Since there's 1, 2 by itself, there's a 2 by itself, we write it back underneath the square root symbol. So that's another way of doing this same thing. You see we got the same answer, 5 square root of 2, right? Let's try that with the square root of 48. So factor tree. What are the factors of 48? The ones that stick out in my head are 8 and 6. Well, can 8 and 6 be broken down further into prime factors? They sure can't. So 8 becomes 2 times 4, and 4 becomes 2 times 2. Now, 6 becomes 2 and 3. All right, now I'm looking for pairs, right? And what I see here is I see a pair of 2's here, and I see a pair of 2's here. The only thing left over at the bottom of my tree is a 3. It doesn't have a pair. Okay, so there's one pair of 2's here. I can write a 2 in my answer. There's one pair of 2's here. So I'm going to write another 2 in the answer, 2 times 2. And then the 3 that's by itself, it has to go back under a radical. So what's my answer here? 2 times 2 is 4 square root of 3. Okay. Square root of 12. Let's try that one. So what are the factors of 12? Let's try 2 and 6. 2 can't be broken down any further, but 6 can. 2 and 3. There's a pair of 2's there, so I can write that without a radical, without the square root symbol. And then there's a 3 by itself. Put a box around that. Anything in a box goes back under a square root. 2 square root of 3 is the answer, just like up here. Okay? So you can do these either way. Okay, so I'm going to do these problems both ways for you. And you can slow down or speed up the video as you need. And you can, whichever way you like doing these is the way you can do them on the homework. I do check to see that you guys are still showing some work. But yeah, look at both ways. Whichever one you want to do, whichever one you want to use is up to you. So square root of 32. Factors of 32 that don't have a factor of 1 are 2 and 16, right? So I can break this up into the square root of 2 times the square root of 16. Square root of 2 stays the square root of 2. The square root of 16 is 4, right? Again, we're looking for perfect squares. And I rewrite my answer with the square root last, 4 square root of 2. We always write it with the radical on the end. Okay, so that's that way. The other way with the prime factorization tree would be if I have the square root of 32, I break it down into 2 and 16, and then I break this down into, well, you can do it a few different ways. So let's say 2 and 8, and then we got 2 and 4, and then we got 2 and 2. Okay, so pairs. Here's a pair of 2's, Here's a pair of 2's, and there's 1 2 left over. Okay? So in our answer, one pair means I write a 2 outside a radical. Second pair means I write another 2 outside the radical. Let me clean that up. And then the one that's in a box has to go back under a radical. So what's the answer here? 4 square root of 2. Square root of 75. Okay, square root of 75. So if you're looking for factors of 75, you would say, well, 2 times something isn't going to give you 75 because we know 75 is an odd number. But if I look at 3 times 25, I see that 25 is a perfect square. So I'm going to break this up into the square root of 3 times the square root of 25, which gives me the square root of 3 times 5. And I, of course, again, I rearrange that because I always want the radical last. Okay, so 5 square root of 3. Now, let's use a factor tree. If I have the square root of 75, I would say, okay, well, this is 3 times 25. And the 25 can break down into prime factors of 5 times 5. 5 times 5, or I'm sorry, 5 and 5 are a pair, so I can write those outside of a radical, or not underneath a square root. And then 3 is all by itself, and that means it has to go back under the square root symbol. So 5 square root of 3, just like we found up above. Square root of 180. So let's see. There are factors of 180. Well, I mean, you can choose any of them. How about, I mean, we could look at 2 times 90. 90 is not a perfect square. 3 times 60. Those aren't perfect squares. What about 4 times 45? Well, 4 is a perfect square. So let's try that. Let's start there. Square root of 180, I can break it down into the square root of 4 times the square root of 45. Okay, that's that's an ugly 45, but that's what it is. That gives me 2 times the square root of 45. Now, here's the thing. Square root of 45, you have to break it down further. If there are factors inside the square root that are perfect squares, you have to break it down further. You're not done until it's broken down all the way without factors that are perfect squares. So what are the factors of 45? I can break this up into 2 times the square root of 9 times the square root of 5. Square root of 9 is 3. So this becomes 2 times 3 times the square root of 5. Square root of 5 cannot be broken down any further. It is in its simplest form. 2 times 3 is 6. So this is 6 square root of 5. That's your answer. Again, anytime a square root has a factor that is a perfect square, it has to be broken down further. So let's look at it using a factor tree. If I have the square root of 180, the way I would do this, and you can start anywhere you want, is I would say, hey, 180 breaks up into 2 and 90. And 90 breaks up into 9 times 10. 9 breaks up into 3 times 3, prime factors. 10 breaks up into 2 and 5. These are all prime factors. Right? So I have a pair of 3's, so I can write 3 in the answer. I have a pair of 2's. I can write a 2 in the answer without the square root. And the only other number left by itself without a pair is the 5. I put a box around it. That has to go back under the radical. So what do we get? 6 times the square root of 5. Just like we did up here. Put a box around your answers. Okay, so I'm showing them to you both ways. Hopefully one way makes sense for you over the other, and you get comfortable doing that. Okay, now square root of 3 over 4. So I can break this up into, because of the quotient rule, square root of 3 over the square root of 4. Square root of 3 cannot be broken down any further. So I just write it as a square root of 3. Square root of 4 down below can break up into 2. This is the simplified form. Okay? We never want to leave a square root in the denominator. We always have to do something to make sure that there is not a square root in the denominator of the answer. Okay? If that's the case, you need to do something different. Square root of 4 over square root of 9. Nice and simple. What's the square root of 4? It's 2. Square root of 9 is 3. You get an answer of 2/3. All right, square root of 98. I'm going to speed this up a little bit. So 98 has, are there any factors that are perfect squares? And the answer is yes. Now remember, perfect squares are, I'm going to write them across the bottom here. 1 is a perfect square, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and so on. Okay? And that's just simply 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49. You get the idea, right? So when I see square root of 49, or I'm sorry, square root of 98, I think what are the factors? And the first one that comes to mind is 2 times 49. Very easy to find. Again, if you got your calculator, if I got 98, I say divide by 2 equals 49. And 49 is a perfect square. So what do I get? Square root of 2 times the square root of 49. Well, what's the square root of 49? Since it's a perfect square, nice and easy. I get square root of 2 times 7. I rearrange that. I got 7 square root of 2. Again, if you want to, you can use a factor tree. Square root of 98. I get 2 and 49. 7 and 7. That's a pair. 2 is not. So I have 7 square root of 2. Oops. Square root of 63. 63 has basic math facts, right? What times what gives you 63? 9 and 7, right? So this is square root of 9 times square root of 7. Square root of 9 is 3. If If you want to do that using a factor tree, square root of 63, 9 and 7, 3 and 3, that's a pair. 7 is not. Okay, square root of 32 over 50. So yes, I can break that up into the square root of 32 divided by the square root of 50, but what I see here is first, before I break it up, what I can do is I can reduce this 32 over 50. Both of those are divisible by 2. So I'm going to rewrite this as 16 over 25 because I could divide both of them by 2. 32 divided by 2 is 16. 50 divided by 2 is 25. That now makes this problem square root of 16 over 25 is this square root of 16 over the square root of 25. Those are perfect squares. Square root of 16 is 4. Square root of 25 is 5. Now, that is probably the easiest way to do that problem. You could also look at it this way. We can say square root of 32 breaks down into the square root of 2 times the square root of 16 over square root of 50 is the square root of 2 times the square root of 25. Okay. Square root of 2's can actually cancel each other out. Square root of 2 divided by square root of 2 is 1. They just cancel each other out. We are then left with the square root of 16 over the square root of 25, which again is 4 over 5. Okay? Let's see. 80 over 4, square root of 80 over 45. We could do some reducing there. Right? What is, each of those has a factor of 5 in it. What is 80? Divided by 5 is 16, right? So this becomes 16 over 9. Right? I divided both of those by 5, which becomes square root of 16 over square root of 9. And that is 4 over 3. All right, square root of 20 over 4. I can break that up into the square root of 4 times square root of 5 over 4. Now, square root of 4 is 2. So this becomes 2 square root of 5 over 4. Okay. You are not done here. Square root of 5 stays a square root of 5. There are no factors that are perfect squares. That's what you have to ask yourself always. Is my square root broken down? So long as there are no more factors that are perfect squares, yes, it's broken down. 2 and 4, though, they can reduce. They have to both not be under a square root in order to do that. So 2 and 4 are going to reduce to 1 and 2. This becomes the square root of 5 over 2. I didn't show the 1. 1 times the square root of 5 is just the square root of 5. 2 stays 2. This is your answer. 5 times the square root of 1 over 25. Okay, well, I can break that down into the square root of 1 over the square root of 25. So 5 times the square root of 1 over the square root of 25. This becomes 5 times 1 over 5. No, let's put that over 1. This becomes 5 over 5, which is an answer of 1. Square root of 24. You can do that various different ways as well. The way I was doing it before, I can break this up into the square root of 4 times the square root of 6. Square root of 4 is 2. Square root of 6 stays square root of 6 because there are no other factors of 6 that are perfect squares. So I just leave it under the square root symbol. I can't break it down any further. All right, hopefully that gets you going. Your homework for today is going to be page 514 through 517, 21 through 46, 94 through 95, and we will do this again tomorrow. This is going to take some practice. I tried to show you a couple of different ways. I know this video was longer, but that's because I wanted to show you 2 different ways of doing the same thing. We'll see you again tomorrow.